So at the end of the last video, we've been working with the N2O4 goes to 2NO2 equation, and we calculated some values for it. We calculated delta G at standard conditions and at non-standard conditions. I've moved that information off to the side here. Delta H and delta S were given in the last problem. Delta G0 we calculated as plus 5.15 kilojoules per mole. It's handy in processes like this to be able to calculate delta G, not standard conditions, but delta G based on the concentrations of these things involved. Those are what we can change the most easily. So we want to know what delta G, whether it's spontaneous at a certain set of concentration conditions. And there is a relationship for this. Delta G at non or possibly non-standard conditions is equal to delta G0 plus RT times the natural log of Q. The same Q that we had back in our equilibrium chapter, QC, works there. So delta G0 is a standard delta G. R is the gas constant. Okay, but we're dealing with G is energy, right? So we need the energy version of the gas constant. 8.314 joules per mole Kelvin, or 0.008314 kilojoules per mole Kelvin, depending on how we're using it. Temperature has to be in Kelvin. And Q is QC, just like we've been doing before. Products over reactants, each one raised to the power of their coefficients. All right, so I'm going to slide this one up. We need to keep this equation in mind. This is the one we're going to use. So for our equation, N2O4 goes to 2 NO2s. If the pressure of N2O4 is 0.50 atmospheres and the pressure of NO2 is 0.25 atmospheres, calculate delta G at 350 Kelvin. So now we're manipulating more than one thing at the same time. We've changed temperatures from a standard temperature of 298 K, and we've also gone to non-standard concentrations or pressures for this. So delta G is delta G0 plus RT times the natural log of Q. So our delta G0 that we calculated in a previous part of this problem was 5.15 kilojoules per mole plus, so if we're working in kilojoules per mole, we need R in kilojoules per mole. Point 0.008314 kilojoules per mole Kelvin. And I'm going to run out of room here, aren't I? Let me move that down. Times our Kelvin temperature, in this case it was 350, times the natural log of our Q expression. Q came from equilibrium, right? Products over reactants. Products NO2 squared over N2O4. So our concentration of NO2 was 0.25. squared divided by N2O4, which is 0.5. So we can calculate delta G for this. This is kind of a real world scenario where you're not operating at exactly standard temperature and pressure, and you're not operating at 1 molar or 1 atmosphere conditions. Okay, so we change temperature and we change pressures. Now we can calculate the delta G and decide if it's spontaneous at this temperature and those pressures. Now when I work this, I'm going to work right to left on one of these calculators. I'm going to say 0.25 squared divided by 0.5 equals, I have 0.125 on my screen, and I need the natural log of that number, minus 2.079, times 350, times 0.008314, equals, plus 5.15. So I get a value of, let me try that again, 0.25 squared divided by 0.5 equals natural log of that times 350 times 0.008314 equals plus 5.15. That looks better. 0.90 negative. So minus 0.90 kilojoules per mole. So at these pressure conditions and at this temperature, delta G is slightly negative. So it is still spontaneous, but not very much. But it still does fit the spontaneous requirements. So the key to this is, at non-standard conditions, if you know what delta G is for at standard conditions, you can use this relationship. Delta G is delta G0 plus RT times the natural log of Q to solve a problem at different concentrations and a different temperature than standard conditions. This is, like I said before, this is a pretty real world example. We see problems like this because these come up a lot. We can't always work at 298, can't always work at 1 atmosphere pressures. Okay? Thanks, guys.